let's take a look at rigid body dynamics. So last time we thought about rigid body kinematics. We thought about descriptions of how things move in rigid bodies. So we had ideas like angular displacement and angular speed or velocity and angular acceleration. We also introduced these rotational kinematic equations. But now we're going to start thinking about why things move in rigid bodies. And in order to do that, we're going to draw a lot of comparisons to the linear world. In the linear world, when we thought about why things moved, we introduced the idea of force. For rigid bodies, the corresponding idea is called torque. Now, just like force was kind of hard to define, torque is also a little hard to define. I'm going to write down the mathematical definition of torque. Here it is. Torque is equal to Fr sine theta. So this symbol, tau, Greek letter tau, that represents torque. F right here is going to be a force that's applied. R is the distance between the location where the force is applied and the axis of rotation. And theta is going to be the angle between the force and R, where we imagine that R is pointing in the direction away from the axis. The unit of torque is the Newton meter, and a Newton meter is a joule. However, we normally write torque in units of Newton meters, not in units of joules. So it's not wrong to say that the unit of torque is the joule, it's just not common. Now, this definition of torque actually comes from a deeper mathematical idea called the cross product or the vector product, which is a very specific type of multiplication that can only happen between vectors, and then it produces a vector. But again, that is beyond the scope of this course. What's important right now is that a torque is kind of a way of either spinning up or spinning down the motion of a rigid body. So, for example, imagine that we have this solid wheel and there is an axis of rotation right at the center. Now, if I wanted to spin up this wheel, I wanted to make it spin, imagine it's at rest at first, well, I would have to apply a torque. And I can apply a torque by applying a force. So let's imagine that I apply a force at a point on the wheel right here on the edge. So that means that I'm applying the force at some distance r from the center, from the axis. Now if I apply the force like so, then the angle between r and the force is 90 degrees. And that means that I'm going to have my torque is equal to r times F times the sine of 90 degrees. Well, the sine of 90 degrees is equal to 1. That's as large as I can get from sine. So that means that I'm going to get the largest possible torque in this situation. If instead I apply the force at this angle, say, then the angle between my r and my force is now about 45 degrees. And the sine of 45 degrees is somewhere between 0 and 1, square root of 2 over 2. Now if I apply the force instead this way, parallel to r, then the angle between r and my force is 0 degrees. I will get no torque in this situation. And that makes sense, right? If I were to apply a force this way, I'm not going to make the wheel spin. Now likewise, I can keep going around and try different angles. If I apply this way, I will also get a 90-degree angle, and that would give me a large torque. However, it would give me a torque in the opposite direction to what I saw previously. And if I applied a force this way, then I'd have an angle of 180 degrees, and I would get no torque out of it, right? I would not get the wheel to spin. And instead of a wheel, I could play these games with, say, a door. So imagine I have a door right here. Let's say we view it from above, and the axis of rotation is right there, what we would usually call a door hinge. And let's say I apply a force like this. Well, if I apply the force right here, very close to the hinge, then I'm not going to get much torque, or at least I'm not going to get as much torque as I could get, because my value of r is small. And if instead I apply a force out here at a larger value of r, I'm going to get a larger torque. And if you've ever pushed on a door on a hinge in the past, you know that if you apply a force right here, it's difficult to rotate the door. Whereas if you apply the force out here at a large value of r, it's much easier to cause a rotation of the door. Now, just like we looked at with angular acceleration and angular velocity, torque can have a direction. So we can think about torques which are applied clockwise or which are applied counterclockwise. And we can also sum the torques. So if you have multiple forces acting at multiple values of r, you can get multiple torques that are acting. And the net torque would be equal to the sum of all of these torques. Now you might be thinking, okay, well, force. We had Newton's second law when we dealt with force. Is there a corresponding rigid body second law? And there is. However, it doesn't look like what you might expect. You might expect that the torque would equal m times the angular acceleration. However, it doesn't. Instead of m, what we have is that the net torque is equal to I times the angular acceleration, where I is something called the moment of inertia. And the moment of inertia is a little hard to pin down, but it's kind of a measure of the ease of changing the rotation of an object. So if an object has a large value of the moment of inertia, then that can be interpreted as meaning that it's relatively difficult for a torque to cause an angular acceleration for that object. And if an object has a relatively small value of the moment of inertia, then that can be interpreted to mean that it's relatively easy for a torque to cause an angular acceleration. Now, how do we calculate this moment of inertia? Well, it turns out the moment of inertia is equal to the sum of m times r squared. So let's think about this in a couple different situations. Imagine we have an axis of rotation here, and then we just have one little tiny point object right there that's rotating about this axis. In that case, well, we do the sum of all the m times r squared. Well, we just have one m, let's give it a mass m, and we have one r right there. So the moment of inertia for that situation is just mr squared. Now let's say we have two masses. They're both a distance r away from an axis of rotation, and they each have mass m. Then the moment of inertia for that system would be mr squared from this guy plus mr squared from that guy. So it's 2mr squared. Now let's say we have this situation where this is the axis of rotation and mass little m is a distance little r away, mass big M is a distance big R away. Well, then the moment of inertia is the sum of mr squared, so it's little m little r squared plus big M big R squared. And let's say we have four masses, all the same radius from the axis of rotation and all with the same mass. Well, the moment of inertia then would be mr squared plus mr squared plus mr squared plus mr squared, 4mr squared. And we could keep going and kind of play these little games. So imagine we have a ring like this going around an axis of rotation right there. And let's say the ring has a total mass m. Well, if we imagine breaking it up into all these little tiny bits, each with a mass, call it delta m, then the moment of inertia then would be each delta m times r squared, and then you sum all of them together. Well, if I sum all of the little delta m's, that means I just get the total mass of the ring. So the moment of inertia for the entire ring is just the mass of the ring times r squared. And if we were to involve calculus, we could calculate the moments of inertia for many different solids, but that's beyond the scope of what we're going to do. Instead, we're going to move on to another idea. We're going to move on to the rotational motion version of momentum, which is called angular momentum. Angular momentum is represented with the letter capital L. Interesting choice. And angular momentum is equal to I times omega, the moment of inertia times the angular velocity, which makes sense, because if you compare it to the linear momentum was equal to mass times velocity. And remember, mass, the corresponding variable in rotational dynamics, is the moment of inertia. And over here we have velocity. The corresponding idea in rotational dynamics is angular velocity. And you can see that the unit of angular momentum should be, what, kilogram meters squared, that's the unit of moment of inertia, times the radian per second. And the radian would go away, so we'd be left with kilogram meters squared per second. And we can keep going with this. So I'm going to write down some equations in the linear sense. So here we have the change in the momentum is equal to the net force times the time. If you remember back, that's the impulse momentum theorem. Change in momentum is just impulse. But also I could write down that the change in the momentum is equal to the change in mv. That makes sense, since momentum is equal to m times v. I'm also going to write down our kinetic energy equation that we remember. Kinetic energy is 1/2 mv squared. And if you remember, we can also write that in a slightly different way. I'll do the quick derivation here. So I'll replace v with momentum over mass. And if I do that, I can derive that the kinetic energy is also equal to p squared over 2m, where p is the momentum. So each of these has a corresponding idea in rotational dynamics and rigid body dynamics. So over here, we have that the change in the angular momentum is equal to the torque times time, right? And we also have that the change in the angular momentum is equal to the change in I times the angular velocity. Also, the kinetic energy that's associated with rotation is equal to 1/2 I times the angular velocity squared. And also, the kinetic energy, in a rotational sense, is equal to the angular momentum squared divided by 2 times the moment of inertia. And just as there are corresponding equations in linear and then rotational motion, there's also corresponding laws of nature. So before we had conservation of momentum, now we can have conservation of angular momentum. One famous example of this is the ice skater. So if we have an isolated ice skater, meaning there are no net external torques on this ice skater, and the ice skater has her arms out and she's rotating, if she brings her arms in, if we look at the moment of inertia, what that does is she's reducing her R for her arms. And so that's reducing her moment of inertia. If she reduces her moment of inertia, well, the angular momentum must be conserved. Her angular momentum has to stay the same. But if her moment of inertia decreased, then her angular velocity must increase, and she spins faster. Also, rotational kinetic energy should be included when we talk about conservation of energy. So when we think about an example where we have a ball rolling down a ramp, it turns out that energy is conserved in this situation, just like we'd expect, but we must include the rotational kinetic energy of the ball. So if we have the ball at rest at the top of the ramp, the only type of energy it has up there is gravitational potential energy. And if it rolls to the bottom of the ramp, it no longer has any gravitational potential energy, but now it has kinetic energy. However, it has both linear kinetic energy, given by 1/2 mv squared, and it has rotational kinetic energy, because the ball is rotating at the bottom of the ramp. And that rotational kinetic energy is equal to 1/2 times the moment of inertia of the ball times the angular velocity squared. Now this is, of course, not a complete picture. For a complete treatment, we need a little more math than we're prepared to go into right now. We need 3D vectors, a little bit of vector calculus. But if you do that, it leads to a lot of interesting phenomena like gyroscopic effects and so on. But again, it's beyond the scope of this course, and hopefully you'll take more physics and see it in a future physics class.